Okay, so hello, in this video, we're going to be kind of refining the model which we introduced in the last video. If you remember, in the last video, we had the model, what do we have? A population is given by an exponential growth model. So essentially, we start off with initial population, okay, and then from that initial population, we either increase or decrease in an exponential fashion, and that is given by e to the rt. Okay, so essentially, it kind of, our R is given by birth minus death rates, okay, and this is kind of what we had in the last video. And we said, this is very, essentially, if I just draw it out, we start at n0, this is n, and this is t. If we draw it out, this is fine. This is fine for kind of up to a certain point. But essentially, what this model is saying, what the exponential growth model is saying, is that as time increases, so should our population. If our population is increasing, then therefore what this model is saying is that we should reach infinity, that we should carry on going infinity. But we can't have an infinite population, right? We just can't have it, just purely because there's only a finite amount of resources available to us on this earth. So therefore, there's not enough resources in order to be able to support a population of an infinite size. So therefore, what we should expect to happen is that actually it should reach this thing called a carrying capacity. A carrying capacity, we call that K. In other words, the population kind of levels off as it kind of reaches saturation point. It can't physically take any more in. So this population model here is fine up to a certain point, but it doesn't take into account that actually the population must level off. And so this is what this thing called the Verhulst model, or the Logistic growth model, considers. Okay, and let me just show you what it is. Okay, it's the same idea again, that the rate of change of population, this is our model, our rate of change of our population is given by our population size times by some growth factor. It's just now we're considering a slightly better version of the growth factor. So, this is the whole idea. If you go back to my first video on mathematical modelling processes, we've come up with the model, we've introduced our parameters, we came up with a good model and we solved it and everything, and we came up with this. Now what we're doing is we're kind of refining it to take, we look at it, we compare it to the real world, and we've seen that actually our population should reach some kind of carrying capacity. So now what we're doing is we're just refining it. So in other words, we're coming up with a better approximation of g of n. And basically what Verhulst came up with was that g of n should be equal to r times 1 minus n over k. Now you may think, hang on a minute, why should that be true? Why should that work? So in other words, what he basically put forward was that dn by dt should be equal to n times this thing. So actually I'll just n times this thing, so n times r times 1 minus n over k. So I'm just going to write it out like this, again just alphabetical order with the rn, okay, times by 1 minus n over k. So all I've done here is I've just put g of n back in there, and I've managed to get this out again. Okay, now why should this growth model work? Okay, why should this growth model work? Well, let's see what happens. Let's see what happens as we kind of, bearing in mind we're expecting our population to do something like this. So we start off at our initial value, n0, okay, and we're expecting our population, if it's increasing, to go something like this, okay? And if it's not increasing, then we should therefore expect, our rate of change to be 0. Okay, so let's have a look and see what happens. So in other words, what we need to consider now is that if as our population approaches 0, okay, what's going to happen to our growth? So g of n is equal to r lots of 1 minus n over k, so r lots of 1 minus n over k. Well, if our n goes to 0, then therefore our n over k is going to go to 0. Okay, our n over k is going to go to 0, right? So therefore what we're going to end up with, our growth rate is just going to be r, which is fine. Yeah? So in other words, what we're saying is that as n goes to 0, so in other words our population is becoming smaller and smaller and smaller, then therefore we can just use, where is it? We can just use this population model. That's absolutely fine. Okay, it's going to be exactly the same. Okay, so it's going to be exactly the same population model if n goes to 0. So in other words, if our population is decreasing, or if our population is kind of relatively small, this is what this is basically saying. If n goes to 0, so if n is relatively small, okay, then this is absolutely fine approximation for our population. An exponential model is absolutely fine, which we showed that actually it does increase in an exponential fashion down here. Before this point here, it does increase in an exponential fashion. Okay, but then what basically saying is that as n goes to k, so let's look at what happens as n goes to k. So in other words, as n goes to k, what we're looking at now this section of the graph here. So in other words, as n reaches its carrying capacity. So as as our population reaches our carrying capacity, so we can't have any more people in our population. You know, we physically haven't got the resources to support any more people. So as n goes to k, right, what do we get? Well, we get g of n. Where is it? So we're considering this. G of n equals r times 1 minus, well, if n goes to k, what we're going to end up with is going to be r times by 1 minus, it's going to be n over k. So as n goes to k, effectively what we're going to end up with is 1 here. Okay, this is just going to go to 1. So therefore it's going to be 1 minus 1, so it's this whole bracket is going to become 0. So therefore our growth should be 0. Okay, that's good. That means it's behaving as it should do. So in other words, when we put it in for dn by dt, so dn by dt, remember what is dn by dt? It's r n lots of 1 minus n on k. Okay, as n approaches 0, so for n which is relatively small, what we just end up with is that, you know, this, okay, which is of course just our population model, okay, so our exponential population model, so n naught e to the rt. That's good, you know, because our population for small enough population, it does behave in an exponential way. But then as n goes to our carrying capacity, our growth rate goes to 0. Okay, so dn by dt, our growth rate goes to 0. So in other words, our rate of change of our population should go to 0 as well. So remember, you know, our rate of change of our population is describing how our population changes. Well, if our population is 0, if our population change is 0, then therefore it means that our population isn't changing. So therefore, we're just leveling off. Yeah, this is the same as saying we're leveling off. So in other words, we have got this effect going on. You've got n, this is t. So therefore, we have got this effect going on. Maybe that's a badly drawn graph, something like that. So we have got this going on. So in other words, for n relatively small, so let's say that this is n relatively small, so n relatively small, and this is now n going n getting our carrying capacity, we get this effect going on. So our rate of change is given by an exponential fashion for n small, and as n goes to k, we do get this leveling off effect, which is good. That's exactly as it has. So basically our model now, we've refined our model to be this. dn by dt equals rn lots of 1 minus k. 1 minus n over k. Just by considering a better growth factor, okay, we kind of get this thing going on, which is good. Okay, so the final little bit of this video is I just want to ask you a few questions, and what I really want you to do is actually pause the video and just have a think, based on everything which I've told you up to now, whether you can actually answer these questions. So basically what we're assuming is that we're assuming a population growth. Okay, we're assuming a population growth. So in other words, r is greater than 0. Okay, so that's population growth. I've got 3 questions for you. The first question is, what happens to the population as time goes to infinity? Okay, now I have already answered that in this video. What happens to the population now as t goes to infinity? So I'm considering this model here. So I'm considering the dn by dt equals rn lots of 1 minus n on k model. Yeah, so my logistic growth model. I'm basically saying what happens to the population as time goes to infinity. Okay. Now the next question is, will the population ever reach the carrying capacity? Okay, so in other words, will it ever reach k? Will my population ever reach the value k? And the final question is, what effect will a larger value of r have? Okay, so I'm going to let you pause the video, have a little think about that. Okay, so hopefully you've paused the video now, had a little think about that at least. Now I'm going to answer it. Well, I've already answered the first question. I've already answered the first question in this video. As t goes to infinity, our population approaches our carrying capacity. Yeah, it's this kind of thing going on. Yeah, it starts off exponentially, but then just kind of levels off. And that's our carrying capacity. So basically, as we move forward through time, so as we're moving forward through time, we're moving in this direction along the axis, which means that we're basically travelling on the curve like this, in this direction, yeah. So therefore, we're levelling off. So in other words, we're reaching our carrying capacity up here. Okay. Now, will the population ever reach the carrying capacity? In the model, technically, yes. Okay, the model says yes. But in the real world, no, we won't. Basically, the population won't be able to grow enough to actually reach the carrying capacity. In other words, the natural forces, unless there's external forces that kind of step in to sort of help that, the way that the world works, normally it stops just short of that. So it never reaches its kind of absolute maximum. If you think about the train analogy, okay, in reality, you know, you can think, wow, this train is pretty crowded. There's no more room on here for anybody else to get on. Okay, but it will never reach the point where there's physically no more room in the carriage. Yeah, because technically the carrying capacity of a train carriage is where every single square inch of space is filled with people. Well, that's clearly never going to happen. Okay, but it will kind of approach that point. So in other words, you know, we're not going to have a train carriage that is completely packed. Like every square inch of space is packed with sort of somebody. You know, theoretically, you probably could get more people in if they kind of, you know, I'm sure you've seen people getting into a Mini, for example. You know, people getting into a car. See how many people can get into a car. You know, people that, you know, if you think about a train carriage, you can have people sort of laying on the ground. You can have people kind of on top of other people. That's never going to realistically going to happen. Okay, so the answer is no. The population will never reach the carrying capacity in practice in the real world. Final question, what effect will the larger value of R have? Well, remember what R is. R is just our growth factor. Okay, it's just determining what will happen, you know, how our population grows. Well, for a larger value of R, that just means that our growth factor is bigger. So therefore, as we move through time, you know, our growth factor will just basically mean that we're going to be growing much quicker. Yeah, if you think about it, if we start off with 500, okay, and if we have a growth rate of, say, I don't know, 2, yeah, then this is time 0. So then at time 1, we'll have 1,000. And at time 2, we'll have, say, what is it going to be, 2,000. Yeah, and we can carry on going, and we'll have 4,000 at time 3. Yeah, whereas if our growth factor was, say, let's say our growth factor was, say, 10, well, at time 0, we're still going to have 500. That's still going to be our growth factor at time 0. Then at time 1, what's it going to be? It's going to be 5,000. Yes, so compared to the 1,000 which we had at when our growth factor was 2. Okay, and then at time 2, we're going to have what it's going to be. It's going to be 50,000. Yeah, that's much, much bigger than the 2,000 we had at the previous time 2, when our growth factor was 2. And then at time 3, what we're going to have 500,000, so 500,000 people, compared to the 4,000 people we had when our growth factor was 2. So basically, a larger growth factor, rather value of R, a larger value of R will basically mean that our population is going to grow quicker.